Hi everyone, thanks for joining the session. My name is Thomas Aubry and I'm a postdoc at the University of Cambridge. Today I'm going to present a new product, the Independent Volcanic Eruption Source Parameter Archive, aka IVESPA, and explain how we are using it to evaluate scaling relationships between volcanic plume height and mass eruption rate. I want to stress that this is very much a collective effort from the IVESPA working group, whose members are listed here, and which is co-led by Samantha Angwell and myself. So first, IVESPA is really motivated by the critical importance of eruptive column models in volcanology. These numerical models can essentially predict the height reached by a volcanic plume from the mass eruption rate at the vent, or vice versa. And then depending on their complexity, they may also account for a range of other parameters such as atmospheric condition or the total grain size distribution. They are widely applied, for example during eruptive crisis, to estimate the mass eruption rate from measurement of the height of volcanic plumes. However, when it comes to model evaluation and development, all these parameters that serve as input and output to the model must be constrained independently, which is challenging. That's why a new working group within the IVESPA Commission on Tephra Hazard Modeling was tasked with building a new database of independently estimated eruption source parameter, and that's IVESPA. So first I would like to give you an overview of some of the main features of IVESPA, starting with the number of events it contains, 134. If you look at other datasets, that's 4 to 5 times more than most of them. I also want to stress that we paid particularly attention to the fact that these eruption source parameters collected were strictly independent, which was not the case in all datasets previously. The role of atmospheric conditions in plume dynamics has gained a lot of attention recently, and in fact in IVESPA we provide atmospheric conditions from 2 climate reanalyses, so you get 2 different sets of atmospheric conditions. Total grain size distribution has also been collected, which again is not the case for all of previous datasets. Critically, we systematically compiled uncertainties, and as you know, anything volcanological has huge uncertainties, but the vast majority of previous datasets did not compile this. And last, I want to highlight that IVESPA is a community-wide effort and that it will have an online and open access database. In addition to this main feature, we have made major efforts to improve the data quality and information availability, which I will detail a bit more. So first among this effort, we had an extensive data quality control procedure in place for each event. We had 2 members of a working group independently reporting each parameter value from their own literature search. Then they revealed their value to each other to reach a consensus. The figure illustrates this process for the total erupted mass of tephra. The y-axis here is the value initially estimated by individual co-authors or data compiler, and the x-axis shows the consensual value that they reached. The dashed line is the 1-1 line. In addition, you can see that these data points have different colors and symbols. They correspond to a new feature of the database, which we refer to as interpretation flag. While compiling data from the literature, we often had to make interpretation or assumption when information was incomplete. For example, when the volume of tephra is provided, but not the deposit density, we have to make an educated guess for the later to obtain a mass. Flag 0, which are the dark dots here, correspond to when we had negligible interpretation to do. And flag 2, which are the light blue stars here, correspond to data point for which we had significant interpretation to do to come up with a value. Now coming back to the graph, you can see that most data points fall near the 1-1 dash line. But there are also some major outliers, such as these data points here, with 3 orders of magnitude difference between one of the initial estimate and the final consensual value reached. They generally correspond to misreporting or partial literature search by one of the data compiler, and it shows how critical it is to have a data quality control in place. If you look at the light blue stars, you can also see that there is generally a good agreement between initial estimate and the final consensual value, which means that reassuringly, data compilers tended to agree even when there was significant interpretation to do. Another new feature of IVESPA that will come particularly handy is that we provide estimates for 3 different types of plume height, whereas previous datasets were only providing a single unspecified plume height. These figures show you the mass eruption rate as a function of one of these 3 heights we provide. The light orange squares are the top height of the ash phase of the plume. Orange triangle are the spreading height of the ash umbrella cloud, and dark red circles are the SO2 dispersion height. Each continuous line is a power law fit, which is the canonical empirical relationship used to relate plume height to mass eruption rate. Now, if you take a fixed value of the mass eruption rate, you can see that, unsurprisingly, the top height tends to be higher than the spreading height, and the SO2 height falls somewhere in between. For comparison, I also showed the Mastin et al. 2009 relationship, which is one of the most popular ones, and it compares fairly well with our new relationship for the top height. And then, although this is a relatively simple improvement, I want to point out that IVESPA potential users can now, such as Volcanic Ash Advisory Center, can now pick the data and power law fit that match the type of measurement that they have for a particular eruption. For example, if they have the spreading height but not the top height, they can now use the orange fit specifically. Okay, last I want to give you some details about how we are starting to apply IVESPA to test scaling performance in predicting mass eruption rate from the top height. So what these 2 graphs show to you is a scaling predicted value of the mass eruption rate as a function of a field-derived value, which is essentially what you get in IVESPA. And the red line is again the 1-1 line. And on the left is a relatively simple scaling that does not account for the influence of wind. And the right is the Doug Ritter and Bonadonna 2012 scaling, which does account for the influence of wind. And if you look carefully, you will see that there is less scatter in the data on the right, slightly less scatter, and indeed the coefficient of determination is a bit higher. So what this means is that wind explains a small but discernible fraction of variability in the mass eruption rate. And on the next slide, I'm going to explore how the residual for this model that accounts for wind depend on other eruption source parameters that we provide in IVESPA. So starting with the magma water content, it's the magma water content that we collected, and the y-axis here again is the mass eruption rate residual, or the model error. And even though there is a lot of scatter in the data, you can see that there is a main trend that is positive and significant at the 99% level. So this means there is a clear dependence of model error on magma water content, which makes sense because this greatly influences the buoyancy flux of the plume, which in turn is critical for plume dynamics. Next, if we look at the distribution of model error as a function of eruption style, this is what we get. So in red is the histogram for all phreatomagmatic events in IVESPA, and in blue is the histogram for all magmatic events, and we systematically compile this eruption style when available. And you can essentially see no difference between the 2 distributions, which was a bit surprising, but it means that there is no discernible dependence of eruption style on eruption style of the model error. And next, same type of graph, but different eruption source parameters. So here we are looking at which volcano the data is coming from. And so in red is Mount Redopt with 24 events, and blue is Etna with 14 events. And now you can see that there is a clear difference between the 2 distributions, which means that either there is a bias related to the way data was collected for different volcanoes, or hopefully there is actually a physical explanation behind it. And in this case, it could relate to the coupling of the plume dynamics to the lava fontaine, as discussed by Evangeline Snee earlier today. So as a summary, I want to point out the IVESPA paper is currently under review and that the website is under construction, and we'll advertise it as soon as it becomes available. But most importantly, you can already access the data by contacting us directly, and we'll provide you with the data set. So you can contact either Sam or myself, and you have our contact information at the end here. And then we are working on providing new constraints on scaling relationships linking plume height and mass eruption rate using IVESPA. And then beyond these relationships, IVESPA includes all parameters required for one-dimensional and three-dimensional plume model evaluation and development. And we hope you will enjoy and use this product as much as possible. Thanks a lot, and I'm happy to take any question.